Hi, so welcome to the first lecture on a set of lectures on the subject of probability and statistics. In this first lecture, we're going to focus on some important definitions and concepts that are necessary to understand the theory of probability and statistics. Today we are going to talk about mainly the topic of sample space and events. So how do we define the sample space and events associated with a certain description? These material can be found on the second chapter of the textbook used in the course. So the main topics that we will discuss today are the definition, what's a random experiment, and then what's a sample space, and what can be defined as an event. So a random experiment can be simplified as an experiment that can result in different outcomes even though it's repeated in the same manner. So basically you are doing the same experiment, you think you have the same inputs, but every time you do the experiment you get a slightly different output. Okay. Now why does this happen? Because as you can see here, for any real physical system that we deal with, there are controllable variables that controls the system. There is a controlled input, right? But then there are also noise variables that affects the overall output of the system. So the output is not only controlled by the things that you think you have control over, but there are other non-controllable noise variables that affects the output. This includes the environment, system variations, even input variations, errors in measuring the outputs. All of these are gonna change the output. Now if these variations in the output are very, very minor and can be ignored, then practically the system becomes deterministic, or the experiment performed on the system, which is providing an input and then measuring the output, is considered a deterministic experiment. However, if the variations are significantly affecting your output, meaning that they make you come up with different conclusions, do different actions, then in this case, this whole system is considered a random experiment. And in this case, right, you need to study the material that we will learn in this course to know how to design under these conditions. So to design such a system or to analyze such a system where the outputs are randomly varying whenever you do the experiment with the same inputs. Okay. So the first thing is, okay, now going back to that example of a system that has some controlled or deterministic inputs that we can control, and it has some controllable parameters. However, it has a randomly varying output because of the non-controllable noise. Okay, going back to that system, whenever you perform the experiment over and over again, you get a slightly different output even though you fix the input. Now all these outputs that you get out of repeating the experiment with a fixed input, so all the possible outputs of that experiment are considered or called the sample space. So it's a set of values that collectively include all possible outputs from an experiment, all possible outcomes of an experiment. So every single output is called an outcome. Okay. Now, sample space can be either discrete, and in this case it can consist of finite, right, or infinite but countable samples or outcomes. Okay, so if the sample space has countable, you can differentiate, you can count them, the different possible outputs, then this is called a discrete sample space, regardless whether the possible outcomes, the number of possible outcomes is finite or infinite. Okay. If the outputs are a continuum, are non-differentiable from each other in terms of continuity, so you cannot count them, okay? It's a continuous possible values of output, then in this case the sample space is called a continuous sample space. And in this case, whether it's a finite region or an infinite region, the number of possible outcomes for a continuous sample space is always equal to infinity, because even if I have the set of all possible values between 1 and 3, which is a finite range, between 1 and 3 is a finite range, but still this is a space that contains infinitely possible values. It can be 1, it can be 2, it can be 3, it can be 1.1, 1.2, 1.3, 1.0001, 2.3, 4, 5, 6, 8, 9, and so on, right? So we have infinitely possible number of values in a continuous sample space, even if the range of possible outputs is finite. Okay. Now let's check the following sample spaces in this example. Okay. So assume that you are randomly selecting a camera and record the times that it takes between taking a picture until the flash of the camera is ready to take a picture again. And we know that a little bit older cameras and flashes or bigger flashes, they actually had this recycle time property. So you take a picture, the flash charges for a while until you are able to take another picture. Now if we say that this time between the flash working and then finishing recharging and being ready to work again, which is called the recycle time, if we just take the possible values of this time, it can be anything, right? Theoretically it can be starting from 0 up to, it can take up to a year, up to 10 years, up to infinity, right? So the set of sample space in this case, in the case of no further conditions are given to you, what are the possible values for that recycle time? They are x greater than 0, which is the set of all positive real numbers, right? So any value greater than 0 up to infinity, right? However, if you were told ahead of time, and this, by the way, is a continuous sample space, right? However, if you were told ahead of time that the flash is known, the recycle time of the flash is known to be limited between 1.5 and 5 seconds. And for all flashes that are produced in this world, it's never small, it's never less than 1.5 second of a recycle time, and it's never greater than 5 seconds. So basically the set of all possible outcomes is the range, the continuous range between 1.5 and 5. And by the way, it doesn't matter in the case of continuity where you put the equality or not in terms of probability calculations. It doesn't really matter. But for discrete, it does matter. So anyways, this is a continuous sample space, and it's limited between 1.5 and 5. Okay. Now, if it's known that you are not interested in the value of the recycle time, but you are interested on quantifying this value or qualitatively describing this value as being low, medium, or high, then the possible outcomes when you measure the recycle time between one flash and the other is that you measure it for this flash, randomly it comes out to be low. You measure it for another flash, it's high. You measure it for a third flash, it's medium, and so on. So what are the possible outcomes in this case? It's only 3 possible outcomes: low, medium, or high. This is a discrete sample space, even though we are still measuring the time. But the way we described the possible outcomes made the sample space in this case discrete, because there are only 3 different ways to quantify or to describe the possible outcomes. Now, if I have some standardization and I say that cameras that have a recycle flash time, which is, for example, less than 3 seconds, are cameras that with good quality and they will be accepted or according to specs, while cameras that have a recycle time greater than 3 seconds are bad or not according to specifications or rejected cameras, then if I want to go and do the experiment of testing the different cameras that I have in front of me, there are only 2 possibilities. The camera is conforming or according to standards, or it's not. So it's either a yes or a no. And in this case, the sample space is still discrete, right? But it was identified as only 2 possible outcomes. So keep in mind that it doesn't matter what's the quantity that you are trying to measure when you are looking at the outcome of an experiment, it's how you measure it as well. So if you are looking for the actual value of the time, you were dealing with continuous sample space. If you were looking for classifying the time as being low, medium, or high, or if you were looking for according to standards or not according to standards, then in both cases, even though you were measuring the time still, but you were measuring it with only 3 possible outcomes or 2 possible outcomes in these 2 cases, which results in a discrete sample space. Okay. Now, how do we describe sample spaces? We have seen in the previous example, the description of the sample space was done by a set, right? So a set includes all the possible outcomes, and that's what describes the sample space. Let's look at a different way of describing the sample space, and this is particularly useful when you have a discrete sample space with many possible outcomes, and particularly if you are doing multi-stage experiment, so an experiment which is done in multiple steps, and then you are looking at the overall outcome of that experiment. So for example, assume that I have messages which are classified as either arriving on time or arriving late. So I have some messages coming from some destination, letters for example, or a message coming from your boss or whatever, and they either arrive to you on time or they arrive late according to their time of arrival, right? Now, if I'm looking at 3 consecutive messages that I have received, right, and classifying them according to being on time or late, what are the possible outcomes in this case? It can be that the first one is on time, second is on time, third is on time, or on time, late, or on time, late, on time, late, late, on time, late, on time, late, late, on time, or all of them are late. So late, right? Now, again, this is one way of describing it, but it's not easy. It would have been much better in this case to construct your sample space by using a tree. The first node is the first trial of the experiment, which is the classification of the first message. So the first message can be on time or late. Now, no matter what happens to the first message, whether the first message was on time, if you look at the second one, the second message can still be on time or late, right? And this on time or late coming after an on time message. Or the first is late and the second can be on time, or the second is late, right? Similarly, going to the third message, it can be for every possibility here for the 2 previous messages, which are 4 possibilities here. The new one, the third one, can be either on time or late. So basically, I look at the first one, it can be on time or late. If it was on time, I look at the second one, can be on time or late. If the first one was late, the second one can be on time or late. On the third message, right, it can be on time or late following an on time, or it can be on time and late following a late on time, or it can be on time and late following an on time, late, or it can be on time or late following a late, right? Now this tree is very useful because again, you only look at every stage for all the possible outcomes starting from the nodes that start this stage. So the first stage starts from a single node and there are 2 possible outcomes. Second stage can start from this node or this node, and for each one of them there are 2 possible outcomes. Third stage can start from this node or this node or this node or this node, and for each one of them there are 2 possible outcomes. So the total number of possible outcomes is the number of those leaves of the tree. This looks like a tree, and these are called the leaves of the tree, right? These, if you count those leaves, you get the number of possible outcomes in your sample space. How do you construct the sample space in this case? Very simple. You simply trace the leaves. So if you go through this branch, for example, it's an on time, this one. If you go through this branch, for example, let me show it to you. If you go through this branch, for example, it's an on time, late, right? Which is this guy, on time, late, and so on. So basically by tracing the different branches across the tree, you can construct the sample space. Okay. So after finishing the definition of the sample space, which is the set of all possible outcomes, and seeing how we can construct or figure out the set of all possible outcomes, how can we construct a sample space? Now we need to look at another important definition, which is called the event. Okay. An event is a subset of outcomes out of the overall sample space. So if I have a particular sample space S, right, and these are all the possible outcomes contained in that sample space. Now if I go and pick out of this sample space a particular set of outcomes, maybe for example if this is the set of all possible numbers between integer numbers between 1 and 100, right, so from 1 up to 100 and integer numbers, if I pick for example the even numbers, right, that's an event E, okay, or if I pick the odd numbers, that's another event, or if I pick the numbers that divides by 3, that's a third event, and so on, right, okay. So the event is a subset of the sample space, right, so it's a subset of the possible outcomes defined by a certain property or some criteria, okay. Now events, since they are subsets, they can be combined by either union, so the union of two events is this E1 and E2, right, or they can be combined through intersection, so the intersection of the two events is this, or the complement. So if this is the set of all possible outcomes and this is my event, then the complement of the event is everything in the sample space outside the event. This is called E complement, the complement of the event E. So these are the possible outcomes in the event E, the subset of the event E, the ones inside, and the ones outside are called E dash or E prime, or the complement of the event. Okay. Now here's an example on discrete events and how you can perform the different operations. I mean, this is a very simple example. Suppose that the recycle times of the two cameras are recorded. So we have two cameras and we have those recycle times, and the recycle times are only classified according to a yes or no, as we've seen in the previous example. So the set of all possible outcomes, the sample space in this case, is the first is a yes, the second is a yes, or the first is a yes, the second is a no, or no yes, or no no. These are the set of possible outcomes, and this is my sample space S. Now suppose that event E1 denotes an event that at least one camera conforms to specifications. Then how many of these are included? You need at least a single yes, right? So this one is included, this one is included, and this one is included, and this becomes your event E1, right? Suppose that E2 denotes an event that no camera conforms, which is only this case. So event E2 is defined as no no. Now suppose that E3 denotes an event that at least one camera does not conform. So you need at least a single no, right? So in this case, the event is this, this, and this. You need at least a single N. So that's your event E3. Yes, no, no, yes, and no, no. If you want to get the union between E1 and E3, so this is E1, this is E3. If you take the union, anything that's common is repeated only once. So you have yes, yes, it appears here, right? Yes, no appears here and appears here. It will appear in the union as only a single yes, no, right? No, yes appears here and appears here, so it will appear in the union as single time, and then no no appears here will appear in the, and that becomes the full sample space because it includes all the possible outcomes in the sample space, right? So the union becomes the sample space in this case. What about the intersection between E1 and E3? You look for the common ones between E1 and E3. So there is a yes no and a no yes. So the intersection becomes only the two common ones, which is yes no and no yes. What's the complement of E1? So E1 includes these. What's in the sample space but not in E1? It's only a no-no. So the complement becomes a no-no, right? So very simple, basic set operations. Now the last thing is a reminder of your basic set theory. So Venn diagrams that can be that represent sets, right? And how we represent intersection, how we represent a certain operation like this. So the union between A and B intersection with C, which is shown here with the shaded area. Similarly, A intersection C and then the complement. So this is A intersection C, which is this white range, and then the complement is everything else which is not in this white range. So the blue part, right? And what's an important thing is something called mutually exclusive events or mutually exclusive sets. two sets or two events are mutually exclusive if they don't intersect. There is no intersection here, right? This and this do not intersect, and hence the intersection between them is the empty set phi, right? So these, in this case, the events A and B are called mutually exclusive. And the last thing is a reminder of some of the important set laws. So the complement of a complement is the same set, the distributive law, the De Morgan's law, which talks about the complement of the union that becomes the intersection of the complements, and the complement of the intersection is the union of the complements. And the last one is the commutative. So if you change the orders, the operation stays the same. That's it for today, for this lecture, and thank you very much.